Спасибо. Меня зовут Илья Матвейчиков. Я читаю
Name is Ilya Matveychikov.
внедрение в процесс
I'm a speaker, as you must have
Linux.
realized. I will be talking about the injection of code into Linux process from the kernel. Let me tell you something about myself.
Работаю с ядром.
I'm a security researcher.
Ну и занимаюсь тем, что
I work with a Linux kernel.
какой-то интересный код для ядра Linux, там выкладываю его.
So I develop interesting code for Linux kernel. I publish it on GitHub.
Вот в частности, несколько лет назад я был в Бразилии на конференции.
And several years ago, I went to a conference in Brazil,
Соответственно, после
talking there about rootkit for Linux kernel.
с этой темой.
And since then, I've published some projects of mine on GitHub. So, for example, there is this project that collects information on rootkit. And so then I developed my own project around the Linux kernel
что может быть удобно для того, чтобы отлаживать,
or intercepting kernel functions,
модифицировать логику ядра, логику работы.
which could be useful for modifying kernel logic in the runtime or debugging your code. I also spoke at PhD several years ago talking about a method for a versatile dynamic implementation of Linux kernel.
Как заставить работать код в ядре Linux без перекомпиляции, чтобы можно было.
So that was effectively about making the same kernel code work on different kernels. So if you follow this particular link, you will find the K-Hook project I've already mentioned, and it also contains a project that my presentation today will revolve around. So it's the one about injecting code in the address space of a process.
Сегодня мы рассмотрим вкратце, я опишу задачу внедрения, то есть для чего это используется.
So very briefly, I will explain why you would want to use it and where. Next, we'll talk about various injection techniques.
Расскажу плюсы и минусы этих подходов, плюс предложу свое решение.
There are pros and cons.
Будет реализовывать внедрение.
And next, I'm going to describe my own solution.
Дальше покажу две демонстрации.
For injecting kernel code in processes. Then I will run a demo. And after that, I'll draw my conclusions, and you may want to ask your questions. So why would you want to do this?
Она сводится к тому, что мы хотим изменить или модифицировать поведение какого-то процесса, да,
Injection of code, kernel code in process is usually driven by our desire to change the behavior of a particular system component.
Цели может быть.
Why would we want to do that?
То есть одна цель может быть.
A multitude of reasons, really. One, for example, to debug a particular process.
Какой-то пробник, чтобы с него получать информацию.
So you may want to build a sample code into the process in order to do better logging. Or you may want to expand the functionality of your application. Maybe you have an application which exists in a binary format and you cannot get a source code, but you want to enrich, to augment its functions.
Например, можно рассмотреть неких акторов, да, которые хотят встраиваться в приложение.
So we can imagine some actors who want to
информации, которая содержится в приложении. Ну, например,
say hack the application to gain access to confidential information stored therein. So think, for example, of an SSH daemon or SSH agent, and you may want to, say, intercept passwords of your users accessing remote servers. Well, then you may want to intercept the functions supporting entry of these passwords.
Если посмотреть на классификацию MITRE по process injection, да, по
If we apply the MITRE classification to the same question,
присвоен отдельный классификатор. Вот он здесь.
we'll see that this subject has its own classifier of T1055.
Скажем так, абстрактную теорию встраивания, плюс.
And the abstract theory MITRE provides is quite good, if you ask me.
Для Windows, например, для.
So they explain what kind of methods are used for different systems, be it Linux, Mac OS, or Windows. I'm not going to bore you with this slide. But if you're interested in the subject, what you will find behind this link is actually quite good quality reads. They will talk about attack vectors. and some such.
Ну, мы рассматриваем Linux, да, в данной презентации, в частности ядро, но сейчас
This presentation will focus on Linux and Linux kernel,
про то, как
but I'm doing this kind of introduction here, so
несколько способов. Первый способ
I'm mentioning some other systems as well. Now, there are different ways you can use. One, possibly the simplest one, is injection through user mode using LD preload, which is an environmental variable.
в этой переменное окружение
So if you indicate in this variable a path to a particular library, then the loader
в начале старта
that gets launched when an application starts will upload this library into the process
может быть, я дальше там
address space.
расписано, пока детально не буду рассказывать. Следующий, соответственно, способ
Now, the next method for injection is a ptrace, which is a syscall.
Ну и, соответственно, это все юзермодная история. А если
So all these techniques are user mode based.
в процесс из ядра,
But if you want to do this injection from the kernel,
достаточно мало информации вообще публичной о том, как это делается.
obviously you'll do it differently. There's very little public information available online. The only public project I found is linked below.
В целом, вот, допустим, первый метод LD preload очень часто используется, ну, там, для модификации приложений.
Say the first method, LD preload,
Практически поголовно используют LD preload метод, потому что
is used a lot
этого метода для юзермод
because there are actually very few alternatives for the user mode, right?
применения. Хотя в том числе существуют проекты, которые используют ptrace для встраивания своего кода. И один из интересных проектов, он вторым, по-моему, представлен в этом списке, но мы далее его коснемся. Итак, возвращаясь к LD preload. LD preload — это переменное окружение, если вы ее поставите процессу и запустите процесс.
So LD preload is an environmental variable.
Пространство этого процесса подгрузится библиотека. Ну, собственно, вы получите свой код, запускаемый в адресном пространстве чужого процесса. Преимущество этого подхода — простота использования. Для этого вообще не нужно обладать какими знаниями.
So the advantages here are that it's very easy to use. So all you got to do is set up this environmental variable, and it's very easy to inject the shared object.
Если они публичны, если они доступны, какие-то символы, вы можете...
And you can easily substitute symbols or functions.
Для отладки, например, нам нужно изменить аллокатор памяти на аллокатор памяти с дебажной информацией какой-то. То есть вот это очень просто делается из LD preload. Но у этого метода есть очевидные недостатки. То есть, соответственно, первый недостаток — это вам необходимо иметь возможность контролировать переменное окружение для процесса. Далее вам нужно иметь возможность...
I'm sorry, I'm responding real quick.
Следующим недостатком является невозможность инжектить в суит программы. Суит программы — это программы с суит-битом. Например, одной из таких программ является утилита ping. Она содержит суит-бит. Суит-бит позволяет этой программе, будучи запущенной, сохранить привилегии того пользователя, от которого она создана.
I'm sorry, I'm back. So with Suite, you need to use the Suite program here, and once the bin is running, it's working. Thanks to SweetBit, because of root and SweetBit on Linux is a major issue. There are so many vulnerabilities related primarily to privilege escalation, and also related to exploitation of issues with Suite. So if you use LD preload, you cannot inject in Suite programs. It is a limitation of the loader.
Инжектить в существующий процесс. То есть вы, например, приходите на систему, там...
You cannot inject in an existing process.
Или SSHD, например. Вы хотите туда заинжектиться, но с LD preload вы этого не сможете сделать.
So with LD preload, you will not be able to do that.
Картинка просто для демонстрации, как работает LD preload. Ничего сложного здесь нет, все это, наверное, знают. Итак, следующий подход.
Now that was just a demo of LD preload. Now, another technique for injection is more interesting than LD preload. I'm talking about ptrace, and it helps inject in existing running processes. And the same method is used for injection from user mode.
ptrace — это системный вызов, который используется для отладки приложений в основном. То есть вы можете с помощью ptrace подключиться к любому приложению, изменить его память, прочитать его память, изменить его состояние.
So ptrace can help you change the state of registers, or reroute a given process somewhere in the memory, or continue execution from any other spot. So the overall algorithm for injection with ptrace is like this. You have the target process, you find its PID,
определяете адрес базы libc.
Then you identify the address of libc base. I'm not really sure why it's there. Then you connect to the target process. You do your code injection. Well, you can read its memory. You can write it into its memory.
Какую-то полезную нагрузку в этот процесс.
Then you find a location where you want to write your payload
В чужой процесс, вы
in the address space of the target process. Then you modify the state of the target process, and then you reroute it
код, который вы записали.
to the code that you've just written.
Исполнение, то есть как бы даете ему
And then it continues to execute.
Достаточно просто, алгоритм стандартный для всех.
It appears very simple. It's actually a standardized algorithm for so many methods that use ptrace. This is a great project on GitHub that supports lots and lots of architectures. One of the big advantages of ptrace is that it's effectively a syscall. It's multi-architectural. So if you're using ptrace to build your own code, you can in fact develop a solution that will work across a bunch of architectures supported by this operating system. And Kubo Injector, for example, I guess is the best one you can find publicly. And you see, it supports so many important architectures. So if you are going to write any code of your own, you should be able to, implement your own logic in the process. So ptrace has got some big advantages, like process control. It's versatile. However, it does require access rights. So by default, ptrace can be used to, so to speak, manage its progeny. See, the advantage is that you can control lots of process, maybe all process if you get the right privileges. I've mentioned already, it's very versatile. It's a versatile system mechanism. It doesn't depend on many environmental factors. In fact, you can connect to process, you can disconnect from process, you can inject code in processes that are already running. However, as a syscall, it can be limited. So in sandboxes, for example, it can be limited. So on Linux, there is a thing called seccomp. So some applications, for example, may block themselves, so to speak, from being traced with ptrace. Also, tracing in containers may be very difficult. So if you have a Docker container, for example, tracing from outside the container will be pretty difficult. Ptrace can also be switched off for a given system. So a system administrator who knows his stuff may decide that, well, this is a totally unnecessary function for the regular users.
Сейчас мы подходим, собственно, к основной теме доклада. Inject из ядра.
So let's discuss the main topic of my presentation, that is injection from the kernel. I've already covered injection from user mode, but injection from the kernel has not been covered much in the previous years, maybe because they believe it's a complicated subject, or maybe because nobody had a need to do that.
Предположим, что мы имеем возможность инжектить из ядра. То есть у нас есть очевидные преимущество, мы находимся в ядре, то есть мы можем делать все, что угодно. Соответственно, мы имеем доступ ко всем, ко всем ресурсам операционной системы, ко всем ресурсам, ко всем процессам, и можем инжектить код как в существующие процессы, так и мы предполагаем, что мы будем инжектить в новые процессы. Но, в принципе...
So we are assuming that we're going to inject both in existing and in new processes.
Некоторые недостатки. То есть ядерный код, он достаточно сложен, он может быть достаточно сложен. Далее я покажу, что на самом деле ядерный код, который...
I'm going to show that it's not as complex as people may think.
Лаконично. Итак, вот проект, про который я вам говорил, который представляет собой попытку реализации инжекции.
So the project I mentioned, which is like the only public project I've been able to find, dates back to 2020. Quite an interesting project, in fact.
То есть, будучи в ядре, что значит инжект из ядра? Это значит, что у вас есть компонент ядра, модуль.
So injection from the kernel means that you have a component of the kernel, a module.
То есть вы ему даете PID процесса, он что делает? Он
So you give it the process PID, process ID, basically.
читает из ядра
Then it will, stop the process, read the stop that will read the file,
процесс вообще всех областей памяти используемых
and it actually has access to all the memory addresses available to the file. So it analyzes the file, looking for the location of libc
эту библиотеку, чтобы потом ее использовать для того, чтобы там найти.
in order to find the library and then be able to find the special symbol for this library.
Этот модуль нашел библиотеку libc, он начинает
Once it has found it for the libc library, it will sort of analyze it.
Потому что в Linux считается не очень хорошим тоном, если вы работаете.
Now, it's considered bad style on Linux to work with files from the kernel. I mean, it's possible, but it's not recommended.
В обычных применениях, да, то есть в самом ядре не так много мест, где это делается. Есть такая возможность. Вот, этот модуль ядра, да, вот этого проекта, он
So this module
чтение библиотеки libc, разбор библиотеки libc, ну, парсинг.
Will do reading and parsing of libc library, and it will also try to identify the address of the symbol
libc del open mode, то есть это
of libc_del open mode, which is an internal function, which if you give it the path, it will try to upload the library to the address space of the process. So once this function has been found, this module will then prepare and write shellcode into the address space of the process using access process VM function. This function is part of the API of the Linux kernel, which enables one to write shellcode to a process. Now, when I say prepare shellcode, what I mean is like this. Shellcode is something that will be running in the address space of a process. So we are assuming that it's going to invoke this libc del open mode, and it obviously needs to know the path. So when I say preparation in my slide, I mean this process of building the address into the shellcode and also indicating the path to the target library. So once all this is ready, the shellcode gets written to the process, and since the process has been suspended, we do verification of the registry state, of the process state in the registry. So you may remember that there is this registry called instruction pointer, and it has different abbreviations in different systems, but instruction pointer is a common register for all architectures, and it contains the address of the next instruction to be executed. So the process has been suspended, as you will remember, and there is a register that contains the next instruction to be executed, and we enter the address of the shellcode there, and then the process is resumed with the sigcont command. What I'm showing next is the structure of the shellcode of the project. It's pretty simple, isn't it? I'll cover it quickly. What happens in the shellcode is like this. The shellcode is whatever starts being executed after the process execution is resumed from the kernel. In other words, we suspend the normal execution of a process, but we need to maintain its state, hence the register. And we also maintain a pointer to the stack, that we do some stack balancing magic. And we also have the address of the library that we want to upload, and we invoke this function and we indicate the address to the library. Then we need to restore everything that happened before we pause it. That's why we have the indicator to the stack, and we also have a similar indicator to the CPU, and we also have the address from which we need to restore it all. In the end, the process is suspended, we write shellcode there, and the shellcode has information required to upload the library, and once we return from the kernel, the process executes the shellcode, uploads library, and then it resumes from the point where it stopped. That's by design, if you like. In fact, in the project I've been describing, this is how it works, but there are some nuances. Now, what's special about the project I've been telling telling you about.
В 2020 году
And again, this is a public project, so it's available on GitHub since 2020.
то, что инжект процессы осуществляется.
And the first feature is that process injection is done as per request. The kernel module I've been talking about has its own PTL.
Отправляете
Common thing, G.
который нужно заинжектить.
So you send the process types that need to be injected.
Автономно получить какую-то систему.
I'm sorry, process PIDs that need to be injected.
Это не очень удобно. То есть, скажем так, для практического применения в
But
некоторых
it's not convenient, is it? So it's not convenient, at least in some practical situations.
побочные эффекты от того, что вы
And I can think of some side effects
стоп, да, и дальше
related to suspending the process
через
with syscall or whatever,
существуют здесь побочные
and then, I'm sorry, with sig stopping and then sig
восстанавливаете,
continuing it.
делаете, а потом этот процесс даете ему возможность продолжить выполнение. Дальше из минусов я бы отметил, что происходит работа
Other disadvantages
из контекста ядра, то есть парсинг вот этого файла.
includes working with files from the kernel context, such as parsing of libc, parsing bitmaps, and that leads to significant inflation of that space. And that may create some critical errors that may, put the kernel into overdrive.
Символьное устройство для управления там работой с файлами из ядра и так далее.
And I've already mentioned that implementation is quite bulky. Now, let me turn
кода в процесс из ядра решил я.
to how I address this issue of code injection from the kernel.
Сделать это.
I have analyzed the experience of those who came before me,
Все компоненты ядра, которые
and I came up with this conclusion that all the kernel components used previously will be required here as well. So I have the kernel module,
это, библиотека,
which is integrated into the kernel using the Khook library.
я говорил, перехватывать символы ядра.
And like I previously said, it helps us intercept symbols or functions in the kernel.
Интеграцию ядро, да.
Now, the kernel module does the integration,
Внедрение кода в
and most importantly, it does code injection in processes. I've also developed several useful payloads,
который будет внедряться
several varieties, if you like, of the codes to be injected in processes. The basic ones I called idle and idle trap. These are the two varieties that help me continue execution of a process after code has been injected.
содержит
Idle trap, the second version,
трап, да,
simply
три природы. То есть,
simply includes the trap instruction.
процесс, да, мы все про отладку говорим. Из дебаггера, чтобы вы просто
So
получили
imagine that
возможность остановиться.
you're doing it for debugging purposes, and then you would want to see everything happening relatively slowly in the debugger.
Object библиотека это,
And then I have another payload for shared object libraries.
изначальный план, который я рассматривал, да, когда думал о том, как бы
So my initial plan, when I was thinking about injecting code in process, was like this. So we have the task struct in the process.
нагрузку туда из ядра.
So we identify memory in the address space, we copy payload there, we modify attributes of allocated memory there so it's executable.
Код оттуда исполнить, да, не только
Well, because we do want to execute code, not just write it there. And then we force the process to somehow execute the code we just loaded.
регистров процесса.
That, however, would require modifying state of process registers.
Нюанс. То есть далее, если вы вопрос себе поставите, да, что делать, например, если
What are we going to do, however, if the code we have injected
причин, то есть мы
does not get triggered, does not get executed? We won't know why.
что нужно делать? Здесь есть разные варианты. То есть, например, можно снова инжектить.
Like, how many times should we try before we decide something has gone wrong? Like, if one injection fails, and two injections fail, how many times should we try in vain?
Неплохо бы попыток
Like, ideally, we would want to have a counter of this injection attempts.
больше не пытаться инжектить, да, например, не хотим инжектить, или попытались там 20
Or alternatively, we've tried to inject and it doesn't seem to work. Maybe it makes no sense. Let's stop wasting our time.
Нам необходимо иметь какое-то состояние, то есть
In other words, we need to track the state.
инжектить, да, код, там
Well,
записывать.
besides just knowing how to inject our code, how to write our code into the address space of a process, we may also want to store the state of the process.
В целом оно будет иметь в себе что? Следующее.
And this state will need to contain a pointer to allocated memory. That's the address in the address space, right? Storing it would be useful. Also, operation status, like a flag. For example, we have failed to inject in the first run. And before we start the next cycle, we need to know if that was attempt 1 or attempt 5, whatever. And that actually requires having an attempt counter. How can we link all this to task struct? If you've done any kernel programming, you must have seen situations like this, when we need to append some meeting information to a given process. I'm not saying it's impossible, but a simple solution will not be elegant. I have found a way which works for me, and I actually think it's quite nice. I will cover it real quickly here.
Поясню, то есть у нас каждый процесс описывается структурой task struct.
So every process is described with a task structure, and it contains struct. Inside the struct structure, we will find an array of values called aux_v. So apparently these are auxiliary vectors. An auxiliary vector of values transferred to the process upon start. So if you've done your share of programming, you certainly know functions like argv, the arguments fed to the process in the command line. But there is also the nfp argument, which is a pointer to the environmental variable of the process. There is another pointer there, which doesn't get used that much.
Я даже не знаю, как правильно назвать. То есть это, короче, некоторые значения.
I'm not sure how to properly code it. These are effectively values that sent from the kernel to the process regarding the architecture this process is running on. Maybe some random values are also sent like this. So this vector is contained in the structure. It has a size, and its size equals to, equals two sets of values.
Этот вектор содержит в себе значение ключ.
It contains their key values, and the methods I'm trying to tell you about
последний элемент этого вектора
will use the last element of this vector in order to store a certain value there. Well, since I'm talking here about 64-bit x86,
в перспективе, да, используя этот метод, хранить
we should be able in the future to store 64 bits related to this process without creating any extra structures or invoking some convoluted logic. Here I'm showing what AXV is and how you can check it out.
Из файла из тем брока его можно прочитать, да? Вот этот вектор, он в бинарном виде. И есть
so the same vector is shown here in binary form.
Переменное окружение LD, подчеркивание,
if you launch, as a LD show XV, you will see this vector decoded like this, shown on the right.
То есть, соответственно, в конце этого вектора мы будем хранить.
At the very end of this vector, we are going to store our own value, which will correspond to the injection state. Next one is the kernel function responsible for array export. aux_v array export. Potentially, it can contain up to 100 records, but usually only 50 records are transferred to the process, which means that the last one will never be seen in the user mode, which means that we can stay hidden. We can easily, store 8 bytes, 64 bits of information. So having found a way to store the state of injection, he drops the subject. I'm trying to show here how state storage is done. We have task struct.
Task struct мы получаем вот этот указатель на ММ, да, на.
And it gives us a pointer to MM, this virtual address space.
Мы просто делаем небольшую математику с.
Then we do a bit of math with pointers.
адрес последнего вот этого вот элемента, в котором можем сохранять данные.
And we get the address of this last element where we can save our data. Now, the slide also says that we got to do atomic capture of state.
Чтобы, ну, у нас много процессорной системы, да, то есть у нас одновременно происходит работа.
Since it's a multi-CPU system, there will be several threads running at the same time.
Что когда мы захотим, допустим, захватить, да, вот это состояние,
So it may easily happen that when we want to capture the state, there will be another thread running on a different CPU, and we may actually get it wrong.
Для того, чтобы осуществить через него синхронизацию. Ну и таким образом, да, еще раз подытожим, мы имеем возможность...
It can be used for syncing as well, for all I know. But most importantly, we can store state information in 64 bits.
То есть, собственно, там 10 строк кода. Достаточно просто все. Да, я напомню, что...
State capturing can be done with 10 strings of code I'm showing right here. And since the project is available on GitHub, I won't waste your time showing the code here. So what can we do with 64 bits? Or 8 bytes? You can argue it's not too much, but we don't need too much. On the other hand, what do we need to store? We need to store the blocking byte. That should require like 1 byte.
Дальше мы хотели бы сохранить в этом состоянии адрес.
Also, we would like to store the allocated memory address within this user process. Also, please remember that when we're using kernel allocator to allocate memory, it will always be line-byte boundary, which means that some junior bits will be zeros and some senior bits will also be zeros, because process addresses have a given range, which means that the mask of addresses in the user space looks like this. There will be lots and lots of zeros there. So we're going to use younger bits for the blocking byte and the senior ones for flags.
То есть ниже вот представлена разбивка, да, по битам, как мы будем указать.
So that's what I'm showing here.
Где мы будем хранить, где мы будем байт-блокировки.
Like where we're going to use the atomic blocking byte and where we'll be using flags. In fact, we can store everything we need with the 64 bits.
Единственный вопрос, да, про который я еще не рассказал. То есть, собственно,
the only thing I have not covered yet is what will be the trigger for injection in the previous project. Injection trigger was the invoking of an external command. Only after that, the module would find the process and would start the injection. In my project, I had a slightly different idea. Since my objective was to have the opportunity to inject my code in any process, I wanted to have a trigger that would be very versatile. I considered different options. IOCDL, for example, was of little interest to me because it would be too selective. Doing it periodically for any process didn't feel too feng shui for me, if you see what I mean. Moreover, you would want to kind of enumerate processes on a regular basis, and it may easily happen that, you know, there will be processes running in the system that won't have your injected code. So I decided that I wanted to use it as a trigger an event that will be generated by any process that we can subscribe the kernel to, and such a trigger is obviously a system call. The only objective of process is to process some data, and that is done through system calls.
На системных вызовах, которые вызывает процесс, это будет неплохим триггером для того, чтобы...
So that sounded like a pretty good idea.
Но нам не нужны все системные вызовы. На самом деле можно было...
Naturally, we don't need all the syscalls. I mean, it would be possible to do that, but that would create significant overheads.
Подумал о том, а какой системный вызов используется достаточно часто. Ну,
so I asked myself, which syscall is the most popular? The top 3 most popular syscalls are read, write, and open, or close.
Я выбрал системный вызов закрытия.
I chose sysclose.
Этот системный вызов, он явился для меня триггером, да, для попыток инжекта. То есть, соответственно,
So I made this one a trigger for my injection attempts.
триггер, мы будем иметь возможность что? То есть у него достаточно
When we intercept this trigger, and it is pretty frequent, right? Every process will be opening, closing things all the time.
процессом
So if we intercept process management when the syscall is made,
состоянием этого процесса в ядре, да, и процесс остановлен, так как он переключился
we will already have captured its state,
на работу в ядро. То есть, соответственно, в user
and at the same time we have control.
могут запускаться.
So in user mode, other threads
Ничего не делает. То есть,
can be launched, but this one will be idle,
ну, и простота, да, вот это вот.
which is convenient, and it's simple. You know, I call it subscription because it's as a subscription. You know, when we have a syscall, it will be pretty easy to intercept it using its name or its symbol using, say, the K-hook library I mentioned before. So the initial plan I described is still missing some elements.
Стейта, да, про который я
In particular, it's missing the state.
Не хватает вот этого события, по которому инжектить. Соответственно, для того,
And the event for injection.
чтобы осуществить, да, работу модуля на полную силу, нам нужно зарегистрировать обработчик вот этого события.
So we need to register the handler for this event, that is for sysclose system call.
Выделяем память в
And once this event happens, we allocate memory in the process. We do copy to user, that is, we copy the payload to the address space of the process. Then we modify the register,
из системного вызова, то есть у него уже
the instruction pointer. And once the process emerges from syscall, it has the payload up there already, it has the modified address, so it can continue execution
еще один момент
and handle the payload.
отличает то, что я сделал от существующего
Another thing that separates what I did from a previous project
для того, чтобы
is the confirmation mechanism.
из процесса, в котором произошел инжект, да, ну там, напомню, крутится наш payload, да, мы его контролируем. То есть
So you do remember, we have our payload up and running, we have control over it, so we can use the confirmation function. So the payload has been injected and it's been executed. Imagine everything has been successful. There can be a mechanism of confirmation for the kernel that everything is successful, everything is over. And it can be based on the same intercepted syscall.
значение там
So if we send back, you know, this magical C1, 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 C1 variable, the kernel module will realize, okay, injection has been successful. We don't need to try injecting anymore. And if something goes wrong,
payload может передать реду, да, реду, то есть повторить. Соответственно, это другой код
we can do redo on payload.
состояния и
I mean, it's a different process ID or handler ID. So another time we have the trigger firing up, we can try the injection again.
так как мы сохраняем
That, by the way, will not necessarily mean
мы всегда знаем, ага, память уже выделена,
allocating memory again, because we have allocated memory already. Shellcode has been written already.
процесс на
So all we got to do is just switch the process to the code which is already there.
еще вот можно, да, можно в стейте можно хранить счетчик неудач. То есть мы можем
All right, we can also maintain the counter of failed attempts.
множество раз.
So this redo action can be initiated many times
Основная часть,
until we succeed.
основная функция,
So next is the main part of the kernel component, the main function which is responsible for the injection.
ну,
Again, it's just 20 lines of code, right? Shown in yellow, highlighted in yellow, is our attempt to allocate memory in the process.
потом
Then we copy the payload to the process. Shown in red are the two areas we modify the state of the register in the process.
процессора модифицируем немножко.
So we do a minor modification here.
Еще в этот регистр
And also,
рес, да, рес это статус возврата.
all right, there is a res, which is like a return state, what we return from the system call.
Вызова, если мы
So when we return from the system call,
процесс, если его переключили на shellcode, он должен в принципе не только
after the target process has been switched to shellcode, it naturally needs to go back to its pre-shellcode state, so to speak,
он оказался.
which is effectively the next space after syscall.
Модифицируем
So shown in red is the line where we
еще и в
modify the instruction pointer,
в статусе возврата, да, из этого сискола.
and as we return from the syscall, we also code information there
Но еще туда же вставляем
that it has been a successful or unsuccessful information, but we also indicate there the address where it needs to go to. It's all available on GitHub in any case.
Сейчас я подойду к вопросу о полезных нагрузках, которые были реализованы.
Let's discuss payloads.
Примеров. То есть первые две полезные нагрузки, они в принципе имеют под собой цель упростить отладку, да,
The first few payloads were designed to simplify debugging and research. I certainly found them useful in my study.
вариант простейшего payload, да, то есть он состоит там из 6-7
So
команд.
this is the simplest payload, really, consisting of 6 or 7 commands. And they do nothing, as you can see. They just return process execution to the place where it should have been without any injection.
Собственно, второй вариант нагрузки — это нагрузка, которая осуществляет как раз
Second payload,
подгрузку из
the one that actually uploads
процесса пользовательской библиотеки. Ну, то есть
user library into the address
основной
space.
целью, да, которая была мне,
That was
чтобы иметь возможность
naturally my main objective. I wanted to inject not just any code,
как инжектить, я вам рассказал. То есть, сейчас
and I've already covered the injection routine, so to speak. So it's time for me to talk now about the structure of the payload.
которая подгружает библиотеку. Ну, во-первых, она должна быть реализована в механизме position independent code. То есть это
So it's got to be position independent code.
да, в таком
So it's got to be pure play shell code, old hacker style, where we don't really know where in the memory it will be located, and we cannot
мы не можем
rely on anything. There are no external dependencies.
функцию библиотеки, потому что у нас
We cannot use, say, libc functions such as open file. We got to do everything on our own, you know? This total self-reliance kind of mode.
найти в памяти процесса библиотеку libc, если она
So we need to find libc library in the process memory if it's there.
множественных, да, в
And like I said, we do have opportunities for numerous injection attempts. So we can start the process, but maybe there is not a single library in the address space, or maybe there are libraries but not libc, and for this pilot we needed it.
не находит libc,
So payloads can be triggered, but if it doesn't find libc, it can send the status redo back to the kernel
в какой-то момент
and
находится libc,
wrap up the shellcode, so to speak. And then finally, you know, when it's triggered again, there will be a libc up and running. That's important because we need libc to calculate the address of libc deal open mode, and then we can use this function to upload our library the usual way.
говорим о таких пейлодах, нам нужно иметь возможность как
Talking about this payload, naturally we need some debugging function.
без
Debugging here with this payload
printf
is done through printf project.
нашел он это, ну,
Again, I found it on GitHub.
printf для embedded платформ.
This is a version of printf function for embedded platforms.
Для этой функции printf, для этой реализации
The external parameter for this execution is the putchar function. So this way you can easily do debugging through serial port or
она использует внутри себя putchar, когда ей нужно
LLDs.
ну, выплюнуть на вывод. И, соответственно, в putchar мы используем просто syscall
So with putchar, all you got to use is a syscall,
в файл. Соответственно, как
like in our right syscall.
функцию внутри
So you summon printf
определенный файл, имеем возможность
as
писать все, что
part of this pilot, then you will be able to write whatever you need into a given file.
libc в памяти процесса.
Now about libc being up and running in the memory, it's pretty easy, isn't it?
Имеем адрес, да, откуда был
Since we have the address
произошел инжекция,
which initiated sysclose, that results in our injection, we still need to go back there.
лежит в какой-то
Now we are assuming that this address belongs to some library. I'm assuming it's libc.
Мы просто сканируем память вверх к
Now we have this address and we scan the memory upwards looking for junior addresses in search for the ELF header of the library that we need, containing the address that we need.
Единственное, что делать,
During the scan, the most important thing we gotta do is check whether memory is available for writing. I'm sorry, for reading.
каким способом, но
I think it can be done in different ways.
мы
One of the ways
такой syscall msync, то есть это syscall, который
is the msync syscall.
какую-то область памяти, да,
So if you direct it at some memory space having a certain length, it will tell you if there is a physical page related to that space.
в
So if we keep using this function before any read attempts,
нам тоже не
well, we've injected our code in the address space of the process. We certainly want this process to keep running, right? So we don't want to address memory that's not available.
проверять, а можно ли в этом
Hence, it's a good idea to check if this part of memory is readable or not before we try addressing it.
Итак, то есть вот эта полезная нагрузка, да, которая загружает сошку,
So this is the payload,
памяти процесса libc,
which will look for libc in the process memory. Then it looks for the functions that's required, and if the function is there, we will use it to upload the library. If it's not there, because libc is not there, for example, we will send the redo status back to the kernel, asking nicely to re-inject the code a bit later.
Сигнализируем ядру, больше не надо нас инжектить.
Or alternatively, we can send the done status so that it doesn't attempt reinjection again.
Компонент ядра, ну, я не беру как бы
So,
компонент
stats now.
для перехвата.
I'm not talking about khook because it's an external component. The kernel component itself was 251 lines of code long.
Бинарный размер
With the binary size
говорит, но тем не менее
is 18,000 bytes,
3 килобайта, да, 3000 байт это текст.
including text of 3,000 bytes.
Полезная нагрузка.
That the code itself is not long. The payload itself is a bit more complex, 436 lines of C code and 363 lines of code in assembler and C code. I'm sorry, 73 assembler, 363 of C, and binary size is 2 kilobytes. That's the shell code itself.
Возможность, да, инжектить shared object в новый существующий процесс.
So this way we were able to inject shared object in new and existing processes using a certain trigger.
Ну и, соответственно, для тех, которые только запускаются, потому что так или иначе, когда-то процесс должен иметь функцию закрытия чего-либо.
Sorry, the particular method we used was pretty reliable because closing happens a lot. Let me show 2 videos, then I'll answer your questions.
Так, уже видим, да? Да, смотрите, я компилирую.
Should be visible already, right? So I'm compiling it.
Вот, дальше у нас listener есть, который будет
And we have a listener.
Из процесса. Дальше загружаю, да, загрузил модуль, соответственно.
Then the module gets loaded.
Что-то вывелось. Если на паузу можно?
And you see something is happening in DNS. So you can say in the kernel log messages indicating there was an attempt to allocate address space. There was an injection attempt.
То есть попробуй заново. То есть не получилось заинжектиться. Несколько раз происходит попытки инжекта.
There were several injection attempts.
То есть, соответственно, мы получаем.
And then see there is act done, which means that indeed everything has been successfully completed. The result of injection is like this. The library that is injected into the ping utility, the suite program, like I mentioned before. So it's sent over UDP. It sends over UDP this short string, which contains injected, the address, ping out, and
Я прошу тогда следующее видео включить.
some other ID, right? Next video, please.
Та же самая демонстрация, немножко модифицированная, работает для инжекта, скажем так, во все процессы.
Now let me show how a modification of this will work for pretty much any process.
Вы увидите, как
So you see module being uploaded here.
Библиотеку, неважно. То есть сейчас
Then the library gets copied.
Происходит загрузка модуля. Да. Дальше мы увидим здесь полотенце, да, сразу инжектов в процессы. Вот мы заинжектили.
So you see a whole string of injections here.
Дальше я сейчас здесь какую-то команду.
I think some command is started here. The system is in a kind of idle state at the moment.
Вот мы заинжектили еще куда-то, веб-бокс сервис там.
Right, you see some services got injected. Then we've been injected in the top.
Потом вот на том правом.
CCD line there.
Зайду на виртуалку.
Now I'm gonna enter virtual machine over SSH. All right, so we are going to inject in sudo now.
Вот, вы видите, то есть мы заинжектились не только в sudo, но еще в какие-то там...
So you see that it has been injected not just in sudo, but also in some auxiliary processes.
Systemd network D уже почему-то, потому что он где-то...
For example, in systemd network D.
На той консоли я сейчас сделал...
Because it made a sysclose call as well, I guess. So now, as I enter the VM, we are going to be, or the code is going to be injected in lots and lots of processes simultaneously.
Так, смотрим вниз сейчас. Это не я так медленно пишу, это почему-то видео так медленно играет.
I'm sorry. I'm actually usually typing much faster. It seems to be a video playback issue.
Должен быть понятен, да, то есть мы
I hope it makes
по
sense.
пути во множество процессов, которые...
So we have been able to inject the code in numerous processes.
Здесь не показан был. Ну, наверное, все на этом.
I guess this is it. Your questions.
Да, спасибо.
Thank you.
Один вопрос, к сожалению.
Oh, right. We have time for one question.
Скажите, а вы не
Thank
рассматриваете,
you very much. It's so interesting.
чем он отличается от конжектора?
Ну,
I'm wondering if you've analyzed the ePPF and what makes it different from kejector.
при
I
прицеплении,
think that ePPF is a kernel thing, right?
можно пакеты в мой юзер-моде, да, там этим я бы...
For example, you can use it to analyze packets in user mode.
Может быть, единственное, можно перехватить функции какие-то в ядре с помощью...
Maybe you can use a PPF to intercept some functions, but the short answer is that no, I haven't considered it. I wouldn't really see why I would want to use it for this particular objective. How about I take one more question? This was short.
Спасибо за доклад.
Me. Thanks for the report.
Статическим бинарям
Did I get it right?
вот этой вот техники.
Кем?
That
Статически собранным бинарям, потому что там, ну...
that static binaries are impervious.
Отчасти правильно, отчасти неправильно. Да, конечно.
You're partially right. Indeed, statically compiled binaries
Липси, либо, да, вот этой вот сошки.
should not be afraid
Но это не значит, что
of such ellipse injection.
статически собранные бинари.
However, we can still inject code in these binaries. It's just a matter of payload, right?
Собранный бинарь, просто payload будет сложнее. Он будет
You're right.
сложнее, да, то есть нам
If
нужно-
you mean that injection of code in statically compiled binaries will be more difficult.
свой reflective loader какой-то для липси.
We cannot really count on libc being up and running. We'll need to upload our own reflective loader and bring into the environment a semblance of libc. Actually, we don't need libc, right?
Подгрузят, да.
Then it would be easier to have a loader for our own library if we're uploading anything there
Хороший
in the
вопрос,
first place.
спасибо,
Thank you.
Подарок.
Great question. You certainly deserve a prize.
Благодарю.
Thank you very much, guys.